Welcome to Thermodynamics, our next unit in chemistry. What do you think of when you hear the word thermodynamics? Hopefully, thermo makes you think of something like thermometer, temperature, heat, okay? All words and things that we will use while studying thermodynamics, but we do need to start with getting you off some basics, definitions, terms, things like that. So by the end of this presentation, you'll hopefully know some good vocabulary-related things. You'll be aware of some of the calculations we'll be doing in the future, but this really is just an introduction. So, a couple of different definitions. First off, thermodynamics and temperature and heat are actually different things. Temperature, you're used to it. It's, how hot it is. If it's 98 degrees Fahrenheit or 57 degrees Celsius, things like that. Whereas heat isn't the same thing. In the English language, we tend to use the two words interchangeably, but heat is actually a type of energy. So, energy is something we will talk about quite a bit in relation to thermodynamics. Energy, by definition, is the capacity to do work or produce heat. Okay, and heat is the type of energy we'll focus on a lot with thermodynamics. A couple of other energy terms just to be familiar with are things like potential energy, which is energy due to position or composition. If you think of the word potential, it's like you have this energy's there. It may not be being used yet, but it's there and available for use. And then there's kinetic energy, which is energy due to the motion of the object. And not that we're necessarily going to do any direct or difficult calculations with this, but just so you're familiar, kinetic energy is equal to 1/2 the mass times the velocity squared. Okay. Again, the potential energy and kinetic energy have really good, in this equation, really good applications in things like physics. If you think about a roller coaster, when you're at the top of the hill on the roller coaster, you have a lot of energy available to you if you start to fall. And as you fall, you start moving faster and faster, so that becomes kinetic energy. But let's relate this to molecules in chemistry. Okay, so these energies exist in molecules and in smaller situations than just uniquely physics applications of them. But nuclear energy is the name for the energy that holds the nucleus together, that keeps the protons and the neutrons together. You have at least a basic recognition of this because nuclear power comes from the splitting of this nucleus and getting some of the protons and neutrons out. And that's a huge, vast amount of energy that's holding this stuff together. Kinetic energy, again, it's still related to motion, but when we're talking about molecules and atoms, it's the vibration of the particles. Okay, and it is directly related to temperature. Okay, the more temperature there is, the more vibration there is. The colder it gets, the less vibration there is. Okay, and we're going to talk about this Kelvin temperature in a moment. Then potential energy when dealing with molecules, compounds, atoms, is the energy that's stored in a bond. When you break bonds, you can release energy. So when bonds are formed, they store potential energy inside of them. Okay? So some other definitions to know. One is the law of conservation of energy, and that energy cannot be destroyed. It can be converted into other types of energy, like potential energy can be converted into kinetic energy, or anytime you lose energy, lose in parentheses or in quotations, due to friction or something like that, it's usually converted to heat energy. Okay? So energy is never lost or destroyed, it's just converted between the different types that are available. And then the first law of thermodynamics is the total energy content of the universe is constant. There will never be more energy than we have now, there will never be less energy than we have now. And that is, again, ties into the law of conservation of energy, is that all energy stays, it just becomes different forms. So, some units for energy. The standard unit is joules, or kilojoules. When dealing with equations, usually they are set up to be used as joules. Okay? Another familiar unit of energy is something called the calorie, though you're not quite familiar with it in this form, okay? But a calorie, the metric unit, is the heat needed to raise 1 gram of water by 1 degree Celsius. It's a very simple thing to kind of remember. Well, the calorie you're familiar with, the one that's on food boxes, things like that, is actually a calorie with a capital C, or a nutritional calorie, and that's actually 1,000 little calories. Okay, so it'd be the energy needed to raise 1,000 grams of water by 1 degree Celsius. Okay. Some useful conversions just to remember is that this one's a big one. To go between joules and calories, there's 4.184 joules in 1 calorie. Okay. Then there's the 1,000 little c calories is equal to 1 big C calorie. All right. They can also call a big C calorie a kilocalorie. Okay. Again, it's all metric, so multiplying by 100 is going to be an easy thing here. And then same thing, a kilojoule. Kilo is the prefix that means 1,000, so the kilojoule is 1,000 joules, just like a kilocalorie is 1,000 calories. Okay. One of the biggest things just to keep in mind is that capital C versus lowercase c is going to be important here. All right. It's an easy thing to miss. Okay. So internal energy, which when dealing with equations will be referred to as E, capital E, of a chemical system is always going to be equal to the sum of the kinetic and potential energies of all of the particles. So the sum of the movement of the particles plus the energy that may be stored in bonds holding the particles together. Okay. Generally speaking, a change in internal energy is going to be the change in heat of the system plus the change in work of the system. Okay. So Q, important letter to recognize, Q stands for heat. Okay. So delta Q, or this triangle, you'll see this a few times, means change in. Alright? Anytime you have delta anything, delta Q, delta T, delta W, it is always the final situation minus the initial situation. Okay? Because what we're doing is we're finding the change in something. So if you want to find the change in heat, if we start out with 100 joules of heat and it becomes 200 joules of heat, your change is 200 minus 100, or 100 joules. Okay? It's important to remember that it's always final versus initial, because what if it was you start out with 100 and then you go to 0 joules? Then your change would be negative 100. But delta is always your final minus your initial. Okay? So, if your change in Q is negative, okay, meaning, think of it, you're losing heat, then heat is going from your molecules, your system, into the surroundings. Okay? Whereas if you have a positive Q, all right, then energy is coming from the surroundings and going into your system. All right. Now, work, again, this is just going to be in a very basic sense, and you'll see in a second why. But work done by or on the system is negative if work is done by the system on the surroundings, and positive if work is done on the system by the surroundings. Okay? So, the big thing with thermodynamics that we really pay attention to, though, is Q, and heat, and changes in heat. So, reactions in which energy flows into the system. Okay? So that means energy comes from the surroundings and goes into the system. So we are losing heat from the surroundings and it's going into our system. Okay? That is called an endothermic process. All right? The prefix endo means in. Okay? So endothermic, the energy goes into our system. So say we have water molecules. We are going to take energy from the surrounding water and we're going to put it into the water. Okay? And then exothermic is going to be the opposite of that. Reactions in which energy flows out of the system as the reaction proceeds. Okay, so we're going to say we have, again, water. Water is going to give up energy to the system. Okay, and then exo, kind of sounds like exit, means out. Okay, so one thing just to make sure that we're clarified on this, that when we talk about this system, we're talking about whatever molecules we're dealing with. This could be a reaction, it could be the glass of water, it could be if we're heating up a piece of metal. Okay, it's the physical thing we're talking about, and then the surroundings are like the air and the other stuff around it. Okay, so in chemistry, particularly when we're dealing with reactions, things that are the size of molecules and atoms, the work or change in work on a system is almost non-existent. Okay? When you take physics, you'll find that work is force applied over a distance. When we think about molecules moving, they're not moving very far, so the change in work is actually a very, very minimal number. So you can simplify that equation that the internal energy, or change in internal energy, really is equal to the change of heat. Okay? So, what this does for us is that we can get a pretty good idea of how much energy is needed to perform any sort of reaction, to perform any sort of, chemical or physical change by measuring the temperature change in the surroundings, because heat directly affects the temperature. Okay? And calorimetry is the technique, the scientific method used for measuring heat exchange between system and surroundings to determine what the change in heat is, and therefore what the change in energy is for whatever it is we're measuring. Okay? Calorimetry is used by food companies to determine how many big C calories are in everything that we eat. Okay? So, calorimetry works by having water, or something that we can easily measure the change in temperature and kind of relate that change in temperature back to energy, surrounded by, or like the water is surrounding whatever reaction it is we're measuring. Okay? So you can make some very simple calorimeters just using a styrofoam cup and another cup, or there can be more complicated one with wires and stirrers, and depending on the precision you need, dictates what kind of situation you would use this in. Okay? The moment I would just kind of understand that a calorimeter is going to have, generally speaking, water surrounding whatever is going to be reacting, and then we use a thermometer to measure the change in heat in the water, because that's coming from the reaction that's taking place. Okay? So, we perform these measurements and get the change in heat from the change in temperature using this equation. Delta Q equals mc delta T, or delta Q, which is your heat lost or gained, is going to be equal to the mass of whatever you are measuring times the specific heat capacity of whatever you're measuring, and the temperature change. Okay? Another thing just to remember is that delta always means final minus initial. Okay, so when we use this calculation here, we're going to be doing our T final minus our T initial. Okay? So, another big thing to talk about is specific heat capacity. So, specific heat is a constant term, but it changes based on the type of solid, liquid, gas that you are using, and it not only varies if you're using different things like water versus ethanol, it can even vary, like water as a liquid has a different specific heat than water as a solid. Okay? So that's one thing. This is something I'd have to give you these numbers. You don't need to memorize these. Okay? One thing to note is that the units, okay, can be joules per gram times degrees Celsius or joules per gram times Kelvin. All right. In this situation, you can use either one, as long as for your change in temperature, you're using both, degrees Celsius minus degrees Celsius. Okay. These do not work, however, with Fahrenheit. You have to use Celsius. But just so that you know, and this is probably the only real mathy thing out of this one that we're specifically going to get into, is that Kelvin, all right, Kelvin is the SI unit versus the metric unit for temperature. In Kelvin, when something in Kelvin degrees equals 0, molecules stop moving. And if they're not moving, which energy do we have none of? Hopefully you're saying kinetic energy. Okay? It's a unique situation, and it's something that is very hard to do. You would die if something was 0 degrees Kelvin because all of your molecules would stop moving. Okay, and you wouldn't be using your ATP anymore. You wouldn't be able to pump your heart because everything would literally stop. Okay? But the conversion is 0 Kelvin is equal to negative 273 degrees Celsius. Okay? Or Kelvin is equal to whatever degree Celsius you're working with plus 273. Okay, so we are familiar with 0 degrees Celsius being freezing point of water. Okay, in Kelvin, the freezing point of water is 273 Kelvin. All right, because with Kelvin, 0 has a different meaning. Okay, so degrees Celsius are 273 degrees bigger than Kelvin. All right, so just to kind of tie this back into what we've talked about before, when you're doing these calculations and you get delta Q to be greater than 0, or it's positive, what that means is that heat is flowing into the system. The system is gaining heat energy, okay? And since it's going into the system, that is endothermic. Endo means in. Okay, and it's going into the system. All right, an example of this would be something like when ice melts. Okay, heat goes into the ice cube and melts it. Okay, likewise, when heat flows into a system, it feels like heat's leaving the surroundings. Okay, which is why ice cools down the water, because the heat in the water is going into the ice cube to melt it. Okay? Endothermic processes, honestly, are the hardest ones to understand. Exothermic ones kind of make sense. Okay, so an exothermic, exo means out. Okay, your heat flows out of a system into the surroundings. All right, these most reactions are exothermic. You feel heat because the heat leaves the system and goes into the surroundings, making everything else warmer. Okay, so an explosion, there's heat or combustion, there's heat that's given off. That is an exothermic process because the system is giving energy out. Okay. Then this is kind of the sum up of really what I kind of want you to understand in just general terms what's going on. Okay, if matter releases heat into the surroundings, all right, heat is energy. So that has to be coming from some sort of energy, all right? It can either come from kinetic energy, which means if we are going to lose heat in the system and it's going to go out to the surroundings, then kinetic energy would decrease by decreasing motion, okay? Or you can release energy by breaking bonds and allowing that energy, the potential energy inside the bonds, to be released, okay? Then if the opposite happens, matter absorbs heat from the surroundings, so an endothermic process, then that energy goes into the system, and it doesn't just have to heat up the system, it can affect kinetic and potential energy. So if the heat energy gets converted to kinetic energy, that's going to increase the motion of the atoms. They're going to move around more. Or heat energy can be converted into potential energy by forming new bonds. Okay? So the big thing from this topic is to know kind of the general terms as far as energy goes and the types of energies, and try to get just a basic understanding about the relationship between these different types of energy, what it means when energy is coming into a system, energy is going out to a system, and how that can affect not only heat and temperature, but also kinetic and potential energy. Okay, so make sure you do the online quiz and see you in class.